we have already known that there is two types of controller that we can design. We can design a controllable controller, or we can design an observable controller. So in this lecture 7, we have designed a controllable controller. In lecture 8, we have designed an observable controller. Okay, and the first thing that comes into mind, because there's about 3 things or 4 things that we want to go through in this video, summarize one. And the first thing we're going to discuss is about the pole assignment. Alright, because we want to shift our poles from for an open loop transfer function. For example, if you want to shift s plus 2, x plus 3 to a closed loop transfer function. For example, if you want it to be s plus 10, s plus 15, you want to shift the poles from here to here, then what can we do about it? Alright, so therefore you use the pole assignment rules to do things. Alright, and how does the pole assignment rules do? It's for a K controller. Alright, you want to find a K controller, right? This is the Ackermann's method you will use. Alright, the Ackermann's method. Alright, this thing over here, if it's a 2 times 2, this thing will always be 1 times 2, 1 times 2 over here. Alright? And then if it's 1 times 3, then it's just 0, 0, 1. The values over here, 1, is always at the last value, while the rest are all zeros. This is for the first part. And the second part, for the controller one, which is KC, alright, this one over here, your rank inverse, is simply taking RCBAB first. This is the rank rule, right? And then if you were to inverse, you're going to introduce 1 over determinant of your A. So initially you have a matrix of A, B, C, D, for example. So you're going to use inverse. If it's inverse for this case, then you're going to have D, A minus B, minus C minus B. Alright, so the inverse of this is this one. Okay, it's mainly based on your RC. Okay. However, for the RO, for the rank for the observer, slightly different. You need to first translate this thing into here first. CT, AT, CT. And then you inverse then. Alright, so the first step for the observable to find K, you have to first find this one first, and then you transpose it. Alright, I think no need to find this one first, but straight away transpose this first. Okay, so I repeat again, you straight away transpose this, and then you calculate for whatever stuff based on your AX plus BU, CX plus DU, that of thing. If you still remember the classic state space model. Alright, so we're going to use this one, and then you have your matrix over here, and then things like that. Okay, and these are all the things that are over here. Alright, well, this thing over here is simply your desired closed loop poles, because if you have desired closed loop poles to be s plus 3, s plus 4, for example, then if you were to evaluate, you will have s plus 7 plus 12, for example, in this case. This is your desired closed loop. If you close loop it, you have this one, for example. Alright, this thing over here is gonna switch. It's gonna switch it to a square plus 7 a plus 12i. This is identity matrix. However, for the observable K, this thing over here is slightly different. Alright, it's gonna talk about transpose. So instead of a square, you have at square plus 7at plus 12i. Okay, and take note that this is the observable A. This one is for the controllable A. Alright, there is a slightly different stuff that deals with the duality system. Alright, where AC is equals to, or ACT is equals to AO. Okay, alright, so then CCT is equals to BO and things like that. These are the duality transformation. So this is for the observable side, this is for the controllable side. Alright, the controllable you can transpose into observable one. Alright, these are the rules, things like that. Alright, and therefore these are the things that you need to take note for the Ackermann's method. Alright, so therefore for the Ackermann's or pole shifting, alright, for the controller side, this stuff going to talk about the Ackermann's, while these things over here going to talk about the Ackermann's. Alright, so we have cleared away the Ackermann's part. and also more in the sense that the canonical form, please take a look. Alright, the very powerful videos I would suggest is this one, the canonical form. Okay, because it contains observable and controllable and observable canonical form, all is within here, and is explained quite fairly useful in, actually not here, sorry, it should be here. Yeah, it should be here. Okay, this is the good video for controllable and observable canonical form. But anyway, this is only the first part. There is pole assignment for Ackermann's. Once you know pole assignment, straight away you know Ackermann, then you'll find your K. Okay, that's all. Next, for a controllable controller, alright, if you still remember for the old time ago, alright, your open loop system is this one, right, for your controller, and then if you were to close loop, you have this one, and then for feedback reference signal, which is for what we're going to design for our controllable controller, you're going to add in the reference signal over here. Alright, we have discussed, alright, and into this system, and then therefore we will have these things over here. Alright, and this thing can be rewritten somewhat, not these things, but the whole chunk over here can be rewritten somewhat in this form. Okay, I'll leave you to think about it. Alright, because this nu and nx is this one. Okay, I'll not leave you to think about it, straight away do it. Minus k over here is over here. So it's just simply trying to rewrite things, but this formation is somewhat neater than this one, right? But you need to know and understand from the PDF file, from the presentation slides lah. Okay, and we know that for the reference signal, normally it is ax plus bu equals to y dot t. Alright, and then x dot t, and then y is equals to cx plus du. Right, this form is for open loop. Right, and if it's for reference signal, you rewrite this form as this form. Alright, and therefore this ni, you can further dissect this portion over here into this portion over here. Okay, and little changes lah. And please take note that if you were to draw that there will be a two lines over here. Two lines means that you are feedbacking a vector. Alright, so please take note that all these lines and things like that. Okay, all this with regards to reference signal to design a controllable controller, a reference signal with closed loop system. This is all within these 3 videos over here. Okay, you can just check it out. And therefore this leaves us the last part, alright, which is the design for observable controller. Alright, the observable controller is slightly longer and takes a little bit more time. But the main concept is this: you have an open loop over here, alright, and because your input is over here, right, you're gonna open loop and open loop over here because there is no feedback. Alright, so therefore this is open loop. And the difference, because you want to design a system that can observe the output of, an observable controller is to design and model a system that is as near as the real system. This is the real system, this is the estimated system. So we want to design our estimated model system as close as our real system, right? And therefore, in order to do that, the error, this is the estimated error state, alright, between your real system and your modeled system. Okay, so the error, if the error is controlled by equals to a times the error of at this state, alright, x and x hat. Alright, so it's x minus x hat is equals to x curly bar t, which is this one. Okay, and for this case over here, this x curly bar dot t is equals to x dot minus x hat dot. Alright, in case you forget or whatever. So this thing over here can never be 0, alright, due to certain realistic system, but however we want it to be 0. So therefore the eigenvalue for a can eventually help us to solve or eventually to help us model our estimated system near to our real system. Okay, we can visualize the output mainly based on the eigenvalues of a. Okay, But however, the open loop system is not adequate enough. Why? It's because you can only observe the things, but you cannot control. So in order to control and actually help us speed up, because the feedback system, the eigenvalue over here can be a slow response or it can be a fast response. But we can only see whether is it fast or slow. We cannot control it, and adjusting it is very tough. And therefore, in order to adjust it appropriately, we use a closed loop system, where instead of this thing, you're gonna attach something like this. They have a big feedback over here, summation, alright, and the feedback over here, which is from your real system, gonna minus away your your estimated system over here. Alright, so this is the difference. At this point, this is minus, this is plus. So therefore, this point, take the real system, minus away the model, and then feedback into your model system, so that you can adjust your model system, which is shown all over here. So therefore, your closed loop system over here has a certain L, right? The certain constants to multiply with your error over here. Okay, so A minus LC can help us to control to shift our controller such that it is easier to control or to ensure that our output is designed to our desired responses that we want. Okay, so therefore the L over here, alright, is therefore goes back to Ackermann's. Alright, if you still remember the poll assignment for the observable system, KO T is equals to L. Alright, the transfer of this KO will be equals to your L. Okay, and therefore this is the somewhat the summarized explanation for your open loop and closed loop system for your observable system. And you want your error to be 0 for this case. Okay, and then you find your eigenvalues for all, mostly your closed loop, because closed loop is more better to control your system, far better than your open loop. Okay, and therefore these explanations are all somewhat talked about over here in this section. Alright, and in order to find the L, you will talk about using this one. Eventually you'll get you'll need Ackermann's method to find your L, because your L depends on how you want to shift your poll assignment, right? Because you want eventually your L over here, your L over here, you want it to actually adjust your model system to the real system. Alright, this is the estimated one. You want to adjust your estimated one to the real one. So in order to do that, you want to adjust using L. Alright, so you somewhat need to use poll assignment also. Alright, sorry, I've been talking for the whole day. You see, my throat is so sore now. But anyway, this is it. Alright, these are all the three important parts. The Ackermann's one. Alright, the design of a controllable controller and the design of an observable controller. Yeah, see you soon.